I hope I'm didn't make any. I hope I know a little bit what I'm talking about in that case. But here, what I don't know about, it's all these details about the mammalian cortex. So, yeah, all right. So maybe I can be so. In the cortex, okay, it's highly folded. We know that because we've seen simulation of the cortex. That's how I know why it's folded. And so there are gray matter, white matter, and the cortical region, which is gray matter, which is highly developed in humans in particular, has is constituted of. So that was my interpretation of the cortex, and it's organized more or less in columns, and so we are going to be interested in columns and also in layers that can be defined that segment the cortex and that correspond in related to different types of cells, of neurons. But here we'll just try to understand how we can have some estimation of these layers without observing the neurons. So this is our goal. So what we want to build is some coordinate system. So we are going to only observe what's happening up and down, and we want some coordinate system that could be a reasonable representation of these layers and columns. And of course, it's going to be a shoot in the dark because we don't really observe the layers and columns, but we want at least our system to be a reasonable guess. All right, so this is as a picture. So trying to have what I'm going to call a laminar coordinate system that we have the transverse direction that will be one coordinate, and then we have this layers. We form some what in geometry is called the foliation that correspond on which we have a two-dimensional coordinate system. So we have two-dimensional coordinate system on each layer, and to know which layer we're on each layer, and to know which layer we are talking about, we have this vertical or transverse coordinate. So that's what we want to build. And we will have a few constraints on how to build that. So just a slide about who are these people who know what it's about. So this is joint work with the CIS group, Center for Imaging Science at Hopkins. The PI is Tilak Ratnanather, and it's a German US collaboration on the neural anatomy of the auditory cortex. So we'll have some images such as that one, by the way, I believe, which come from data provided by the German group, which is at the Hanover Medical School. I just gave this talk at Dachstuhl last week, and people were much more excited.
Deaf cats.
No, deaf
cats.
Yeah, well. No, it's not about the deaf cats. It's just about the German collaboration. All right. So let's have some mathematical notation. So I have my two surfaces. I am going to represent them as curves here, but I have here S0 and S1. What I want is to build this coordinate system. So now I have some 3D region in the space, and well, it's not really. It's going to be well, it's huge. So I'm going to here consider build my coordinate system from the base surface and the transverse line. So I have x on the base surface, and I have t on the transverse line. And if I'm going given x and t, I can go along the transverse line and get a point in between the two surfaces. And this I'm going to call psi of t. Okay, so that's how the coordinates are built. So here I have an x prime, I have there some psi of t prime x. So I want to build this coordinate, so it's going to be a function from 0, 1. I'm going to assume that the time goes from t equals 0 here to t equals 1 on S1. Such that, okay, we start from S0 and at t equals 0, we just have the entity. And at the end, I want at time t equals 1 to fall onto S1. The other constraint is, did I write it? I haven't written it here. So we are going to interpret the, when we fix t, we will have this surface, so that's t equals t0, say, fixed. So we will have an intermediate surface that will interpret as some definition of a layer between the, I think I have to redo the whole note. Between the surfaces, and because people often refer to this, and I believe I have two typos here, it should be psi, not t. The transverse line, we are often called the streamline. We say that from time to time. And then there's one quantity that we are interested in getting from this foliation. It's the length of these streamlines, because this is going to be for us a good way to compute, to give a definition of the thickness of the cortex. And this is not something which is well defined, the thickness, where I mean, what is up or down, how do you define how thick the cortex is? So there are several definitions on the market. This will be ours, the length of the streamlines associated with this foliation. So the cortex thickness is quite important in the analysis of degenerative diseases.
So there are 6 layers, and they're anatomically separate, and you're not going to assume anything about the anatomy? Is that what I understand?
Well, we are not going to assume that we know them, because we don't see them. It's going to be, we just know the surfaces. So we want to have something, so we'll see that, going ahead, there is an equivolume constraint that is at least hypothesized, it's boxed hypothesis on these layers. And so we won't know exactly where the layers are, but we want to build equivolumetric. Our own equivolumetric layer.
Each layer and the layer above and the layer below have the same volume. Is that what you mean by equivolumetric?
It's more, no, it's that when you are, so if you look locally here, so if you take the surface element here and the same surface, I mean, an optical, at least in area, surface element there, the volumes here or there should be rough.
That's a hypothesis.
That's a hypothesis, which it seems to be.
Is that really true for the?
As I said, that's what my collaborator. But that's this is from Bach. It's not exactly true, but it seems to be reasonable, at least visually, when we look at the data, when we histological data. I mean, it's an approximation. So at least we want to have that. And of course, we won't know where exactly the layers are if we don't have more information. We don't know the exact thickness of each layer. But it's going to be some way to at least say, all right, I'm going to hypothesize that my layers is at some t that I will have to determine. And the goal is to then go back to histological data and try to find the best t that defines the layer. And we will have, in this project, it's an interaction between histological data for the cortex, for this cat cortex, brains, and MRI imaging.
I guess one thing that's interesting, so for the histological data, if they're making sections, like the physical process of making a section, you don't know that you'll always be making that sort of normal to the surfaces, right? But if you can extract surfaces, say from the MRI data or something, then you can always make sure that mathematically streamlines are normal to both surfaces, right?
Well, one of the difficulties is that there are many ways to make sure that we don't generate smooth surfaces. But yes, it's true. So there is more than one solution.
But I guess fitting back to using the experimental data to test that might
So
introduce
there is
problems
a
because-
difficulty. I mean, it's
Yeah.
a research project. So we are going to try to find reliable ways to glue together this histological data. We already have some experiments like that. And so once we build 3D images from histological data and then try to compare.
So what you're asking is precisely what is the correct mathematical foliation, because you can construct infinitely many foliation for this problem.
Yeah. So we'll do one.
You should. Yeah.
One that and
the other option
there are
would be look at the
approaches.
data and see what.
Yeah, and we have our favorite method. I mean, essentially, we want to ensure smoothness, be sure that we have no changes topology or way of that. So we have one way to do it, and it's that.
Yeah.
And even our way is going to be parametrized, so we have more than one solution. Okay. But I just want to point out that you are actually asking me questions about neurology in your imaging. You can see how uncomfortable that makes. Okay, so as just remarked, there are several methods already on the market that do that, and probably maybe the most natural when you want to build this kind of foliation with surfaces that we streamline to our perpendicular to the surface is to take level sets of a function, and that was a method that was so the general framework is, well, you have your two functions, you have your two surfaces, you have, so again, make another picture. You have a zero, simple, and what you start from is a function, so you should that you have a function defined, so here you have this open set, and the assumption in all these methods is usually that you have closed surfaces. We have the set omega, which is the set between the two surfaces, and on omega you have a function. So for each x in omega, you can compute you assume that this function is such that its level lines are submanifold or sister surfaces in R3, which requires this kind of assumptions, and you assume that the zero level line is at 0, and the one level line is 1, and when you have that, well, you can look at the level sets function, f equals t, and what you know is that the gradient of the function is perpendicular to its level sets, and so you can define streamlines in that setting by just taking going along the gradient. So if you want to define the thickness, you have to build your curve with a special parametrization, which is the gradient of f divided by its norm squared. You integrate this ODE, and what you have at the end is something that the length of the streamline is the one way to estimate the thickness. And so that was probably the most commonly used method, was introduced by in this paper in 2000, in which what the author suggested to do was to define f on the boundaries, because that's part of the constraints, the requirement of the method, and then solve the Laplace equation in between to get some smooth motion between the two surfaces. So that's one of the methods that are used. Another one, which is also working with closed surfaces, is it's slightly different notation. You have, again, the interior surfaces, and you assume that it is the boundary of a volume omega 0, and you have the external surface, and you assume that it is the boundary of a volume omega 1. So omega 1 also includes omega 0. And what you're doing is now trying to find a diffeomorphism phi that takes an x, or actually a flow of diffeomorphism, x in omega 0, and returns when you flow the diffeomorphism up to time 1, so the flow means the diffeomorphism is time dependent also. You get you end up on omega 1, and now if you take your diffeomorphism at time t, and you look at all the images, you get an estimation of your the layer, and the cortical length is again the length of the streamlines defined.
In this one, you don't guarantee the perpendicular.
No, that was not possible. So, okay. So, two remarks on this method, that they are based on volumes. So you have to you need to have the interior between the two surfaces, or the interior of each surface, and so they are relevant when you have closed surfaces.
Why
surfaces that
for the last one you don't need to have the close.
Well, at least for the one because they were doing image matching, so they couldn't do it. That was binary volume, so it was not based on surface matching. So here we are going to use surface matching, and we are going to add the constraint that the level lines, the streamlines are perpendicular. So
is the issue here just that you're trying to measure some way to measure the thickness?
well, we want that and the coordinate. The coordinate system is we plan to use it. It's not there yet, but we plan to use it, for example, to be able to build some structural models for deformation of the cortex, which would be better than the kind of model that we are using. So we want this coordinate system. The first byproduct is this. The second will be this equivolumetric. Okay, so here's LDDMM, and this is what the acronym is. As I said, in case it cannot be worse. So I don't want to spend too much time on this algorithm, but what it does is that it deforms an object, any object, not any object, but a wide range of objects. It deforms an object into another one by advecting it with this kind of equation from the time 0, that would be the object at time 0, to time 1. And this transport is controlled by some velocity field that is called V, and this velocity field itself is optimized with some regularization. So that's in a nutshell the definition of LDDMM. It's an optimal control problem that takes an image Q0, moves it according to this equation toward an image Q of 1 that is, because there is a penalty term here, close to Q1, our target, and it optimizes the motion by minimizing this, which is the measure of smoothness of the evolution. So,
It's not an image in that case.
no, in that case it's an embedding. So I didn't, but oh yeah, that's here. Yeah, okay. So it's in that case that would be the one we are going to implement is between embeddings. For images, the equation is different. The advection is not the equation. All right, and the reparametrization invariance is to handle one of the remarks that Eric. It's terrible. Okay, growing old. And that these embeddings, they come with their own parametrization and they don't have to match it, so you have to do a parametrization invariant to be able to compare. Okay, so that's what I was saying about LDDMM. That's probably my shortest description of LDDMM ever. What we want to keep from it is that, so because we have this time evolution, it returns a time-dependent embedding, which means that it's going to be a time-dependent surface between the initial and the final one. It also returns a time-dependent diffeomorphism, and actually the method that I described earlier implemented a version of LDDMM to get the diffeomorphisms. It returns a streamline, and it returns also something that can be computed on the fly, like morphometric quantities of Jacobian determinants, so changes of area, changes of volume. So okay, so that's some references. If we apply this without requiring that the streamlines are perpendicular to the surfaces, we get something that may have strange behaviors, like the surface going forward and backtracking. This is not the kind of thing that we want. So we can modify the algorithm by adding constraints. That was one of the main subjects of the PhD dissertation of Sylvain Arguillere with Alain a few years ago, and so one of these applications is trying to get this perpendicularity constraints with for streamlines, and if we do that, we get a more complicated version of LDDMM. Let's see the LDDMM, and this is one slide about the numerics. The only thing that I want to say is that we're using augmented Lagrangian for handling the constraints and BFGS for the minimization algorithm, and we have some discretization scheme, and I don't go any further here because I don't need to. Here are some results. First on synthetic data, and I really have to show you that because it took me forever to just generate these surfaces. All right. So you see that would be S0, that would be S1, and these are the streamlines returned by the algorithm. That's what you kind of expect, and this is this estimation of the thickness. Kind of makes sense of, as you can guess, blue is smaller and red is bigger. So real data is harder because it's not as smooth. We have this cortex that folds. I mean, so the interior surface can be very irregular, but it still works. It's kind of reliable compared to other methods. The thickness that we obtain is a smooth and rather robust estimation of thickness, and relative to people who know how thick the cortex should be, that makes sense. So this is reasonable, so some more. And so let me, in the 10 minutes, does I have that? You were not paying attention.
And don't subtract.
So, well, whenever I have that, let me go now to this hypothesis that I already started describing here, which is the
13 minutes.
Some time for questions. So, describing this equivolumetric hypothesis. So, if I take a piece of surfaces, let's call it sigma here, on the bottom surface, I can follow the streamlines that start from sigma, and what I get is some volume, and that's just going to call that cortical tube. I am not that, it's not me, but what is referred in the box hypothesis as a cortical tube. And so now we have these layers, and I've connected each other that I have. So I have two versions of a cortical tube here. There. So the assumption that is made in this hypothesis of Bob is that when you take the same surface area on different parts of the cortex, then the volumes of the intersection of the cortical tube and the given layer cannot be constant. There's some variation of thickness, for example, but it's very slow and it's almost constant. So this is what we will try to compute, and we are going to assume that we start so that we start from the output of the previous method, which was this coordinate system. Once again. So I have, what I just, if you write the parametrization, Q0 and Q1, and what I have is in between a Q of T, and I have streamlines that I, by using my constraint optimization, are perpendicular to the function Q of T. So what I'm going to do, so that this is already a laminar coordinate system. I'm going to parametrize it by doing a change of type so that it satisfies box hypothesis. So this is what is written here. So we have this coordinate system, phi here, and it has nice properties, but not necessarily satisfying the equivolumetric hypothesis. So what we are going to do is change the speed at which we travel along each period line. So now we have this estimation. We are going to have different speeds at every point, and this is formalized by having a reparametrization just in time of the parametrization, but the time parametrization depends on the point x. Remember that x is always on the original surface. So we are going to reparametrize the transform phi into this phi tilde, so that when now I'm considering surface patches, I have something that satisfies the box hypothesis. And we cannot have this equivolumetric constraint satisfied exactly, again, because we have to end up, we couldn't, I mean, that would be impossible, we couldn't end up at with the right thickness, but at least instead of being a constant function of t, we are going to assume that it's a linear function of t. T. Yeah. So we are going to assume that we move linearly in time. So the volume here after reparametrization is for some alpha completely smooth linearity. So then, and really that's the need for me to go through the details, then the rest is just algebra. You write these constraints, you recompute this volume by doing a change of variable, and you find after some work that, well, you find some formula that involves the normal to the surface, the original estimate V that was returned by LDDMM, and the surface element that gives you what actually is the inverse reparametrization. Once you have the inverse, you can go back to the original.
Excuse me? So if I'm considering on S0 a very small point, right? So everything translates to the length of your normal fiber, right? So I'm saying that if you, this leads to computing the length of your normal fiber if you're considering a very small piece of S0. So now you're saying that reparametrizing.
No, that's the volume that comes into it. If you do the change of variable, you see that in this change of variable you have more term that comes, not just linear. So it's about really, it's not just x, but it's a dx.
Yeah, but since you're integrating in time, this dx is always going to be the same.
No, because time depends on x, so there will be derivatives.
Okay.
When we compute, sorry, I did really skip this computation. The change of variable is here, and so you have, well, you should imagine that you have a parametrization of your baseline surface, and you have to change the variable. You have several terms, derivatives, because this x here appears twice. And so it's not just a change of time that would be constant with respect to space. It's a change of time that depends on space. So just to conclude, here are our first results. And so it's interesting to see, that's the interest of doing some synthetic example with that it's easier to compare. So the blue surface here is actually the surface that is estimated by LDDMM for what it's worth. It's the surface at time 0.5. And you can see that at time 0.5, this LDDMM is almost there in the low thickness region, and it's what's going to happen is that after 0.5 it's going to grow the rest, but it's almost there for small thickness. If you reparametrize, and surprisingly using this hypothesis, you get more sensible surface, which is the right surface, and that would be the mid layer. But according to the equivolumetric hypothesis of this interspace between the surfaces. So here are some estimates. So the one that we correspond to the box hypothesis is the green surface, and again, they look like what people expect for cortical layers. It's, I mean, if you don't have them, it's a reasonable way to guess where they are. Of course, you have to know what thickness you have to expect of the fields, but that so these are just the surface by themselves, more results. These are really preliminary.
Which is the red surface? The green surface is the...
So the green is the equivolumetric. The red is the one that is just estimated by the first, so without the change of line.
So it's naive, but I suppose it's very simple to flatten then the structure if you want, say, to have like a projection map.
In that case, I believe we haven't tried. We usually work with triangulated surfaces, and we never have to really.
No, but if you want to compare different individuals for the size of whatever area, it's very difficult to do with the foliation.
So, but that's what we usually do. So that there are several ways of doing this. We usually don't flatten because flattening creates too much distortion. So what we try to do is to estimate an intermediate template average surface that looks like the surface that we have in the data, and rebuild everything on that surface, transport everything on that surface. That's the same as flattening, except that instead of taking the plane, we take a surface that looks like the one that. There are other methods. You can actually compare data plotted on surfaces directly, and these are things that are not developed with Nicolas Jarre, but even beyond that, just so using templates which are not necessarily flat. So here's my conclusion, just saying that the most important part is this is work in progress, and most of it is not published by. So please note tweeting. And well, that's just surprising, but just say thanks.
All right. Questions?
At the end, when you recompute the surface, so you're losing now the normality condition.
No, it's there. I think maybe not.
No.
Yeah, no.
Yeah, the normality is good.
So can you just try to incorporate this block condition in the first stage where you could try to.
It's higher order. It's a very nasty constraint. So in principle, you can write this as a constraint.
Yeah, because
it's very painful as a numerical. It's a yeah. It's just that it's not optimal, but it's simpler than doing everything. That's really painful. Oh, of course, you're using TensorFlow or whatever. So.
In some sense, the motivation of detecting all values and measuring thickness of would be to do it in a live patient. I mean, like a real patient who's alive, right? How do you know how thicknesses are measured in life, or like?
So right now, I think the state of the art, the method that is used the most is based on the Laplacian. So on the live patient, I mean, you take an MRI, you segment out the cortex, use FreeSurfer most of the time. And FreeSurfer has its own estimation method, which is not Laplacian based. But there are tools for that.
But if you have just the images and you take a cross section and you measure the heights, would that be different in some sense?
Well, it would depend a lot. I mean, first the height. I mean, how do you define the height? When you have that, what is the height? This, that. I mean, should you take it's tricky. Depending on the thickness, it's tricky. You want to be perpendicular, so maybe you want to be perpendicular there, but maybe it's better to be perpendicular from there. So it's a tricky problem. So that, there's no unique solution.
Actually, following from that and looking at the empirical data, I got the impression that the grooves are slightly thinner in the cortex. Is that something that the grooves, the valleys, is the cortex there thinner than in the more outer parts?
So
It was one of the images that works.
yeah, it seems like
Laura, can I ask you something?
well, you have to.
It looks like a tube.
There's no way to get that because of the
Suppose you have done this very well on a template, that you have two surfaces and you've done the lamination and stuff. Now you get a new surface. Can't you do some sort of strange illustration and just bring the laminar surfaces to the new surface just by transferring the illustration?
So that could be.
And it shows some volume preservation.
Yeah, the thing is, when we do registration, whether it's based on services or on images, the homology registration region in which we don't have any information of, what we do is just an interpolation. What we do is essentially register the two surfaces and then interpolate. Have an transport the layers on one side by interpolation.
It's the same thing.
Maybe it's enough. Maybe it's enough.
Can I just, so how about, I know Ratnanather did this for some other case, he did this with Poisson equation with two boundaries. He was doing this, he called this the Darcian coordinate system. You have the perpendicularity,
Yeah.
the patches have some similar areas. He was doing 2D. And he did this with Poisson equation with two boundary condition S0 and S1.
Yeah. So it is this Jones method. Well, when did he do it? Because that would be great.
Well, so this must have been 2009, 2010.
Oh, okay. So it's after later.
Yeah, this is planar shapes. He was doing his growth model, the grid
Okay.
model. He needed a coordinate system for that.
Yeah. So this is.
Okay. All right, let's thank
So
you.
if Wolf did that, maybe we should let
If that's your criteria, you can't publish anything. He did a lot. Let's thank Laurent very much. We have a right? Yep. All right, we
25
have
minutes.
15?
25.
25 minutes. So